things now that we have become. So we've got nearly 100 people here. That's fantastic. So some of you will have been watching me making the videos and putting those up to explain the work. So the idea behind the webinars is obviously that it's going to be very similar. I'm going to talk it through in the same way that I did in the videos. The difference is that it's live, and that has some advantages. You'll notice you've got a little box that says Q&A. Your Miss Wanstall is here as well. And if you type a question into that box, Miss Wanstall will be able to see it and will be able to help you. All of the slides that I'm using now will be posted in your classroom exactly the same way that they were when we made videos before. So the slides will be in your classroom. So all of the work is on these slides and they will be in your classroom by the end of today. We are recording this, so the video will also be there for you to go back over if there's anything that you get confused about or that you need to go over again. So hopefully that's going to make it easier for you. Now, these are saved in the webinar folder on the school Google Drive and places like that. But for your work, when you're answering them, so if you're watching this as a recording now, a little bit like telly, if you're watching this on catch up, you still need to go back to your classroom to be able to do the work that you're going to hand in. Okay, it's really important that you go back to your classroom to do the work that you're going to hand in. So we've got a bit of a difficulty in doing this. There are classes that are in different places. So from next week, all of the work should be new for everybody. Today, some of this work is going to be revision for some classes. Some of it is going to be new, completely new for some classes. So this is to cover everything. I'm going to go through three things. I'm going to explain circuits, I'm going to explain series circuits and parallel circuits. If you've done the first bits, this is a bit of revision for you as we go through that. But by the time we get to the end, no one will really have done all of that. Fantastic. So let's get going. So what do we need to make a circuit? Well, we can make a circuit out of any things that we can connect all the way round. So here we've got a cell and we've got some wires and it's connected to a lamp. So that's a nice, simple, straightforward circuit that you've probably built in primary school and probably built in Varndine at some point as well. Okay. So what actually is a circuit? Well, a circuit is a path for electric current. It's complete, it mustn't be broken. So it will only flow if there is a path of a conductor, something that allows electricity to pass all the way around. And we usually use metal. In fact, we use copper for wires because copper is a very good conductor. And if there is any gaps, it can't move. So before we go any further, I've got a quick question for you. So I'm going to put a poll up. No one can see your personal answers. I just get a percentage as to how many people answer different things. So before we go any further, see if you can answer that for me. Okay. What is the name of the negative particle in an atom? Brilliant. It's going well so far. Gosh, it's going fast. You're all quick off the mark. About half of you have voted now. I'm going to give it about a minute in total. Nearly all of you, just coming up to 100 people voted. So, and we're up to 30 seconds. So if you're still thinking, I'm going to give you about another 10 seconds. So, and we've just gone over 100. So we've got nearly 90% voted. Absolutely fantastic. And the 10 seconds are coming to an end. So if it's a last ditch effort, click something now. And it was an electron. Excellent. And 76% of you got that right. So it's an electron. So the thing that actually, the path is for the electrons that are flowing around. And an electric current is a flow of electrons, a flow of negative charges. Okay. So the reason it can only get all the way around is if there's a gap, the electron can't get across that gap. It has nowhere to go. So there are some words that are really important for us here. So an electric current, I've just said, is a flow of charge, negative particles, electrons. That's why we call it electricity, because it's the electrons flowing around our circuit there. Now, the other one that we talk about is people sometimes talk about voltage. Now, I don't really like that because firstly, it's not correct. It's actually potential difference. So this is a measure of how much energy those particles have. And we measure it in volts with a voltmeter. That's why people sometimes call it the voltage, but it's the potential difference. It's how much energy they've got. So if we push them harder, we give them more energy, then the voltage is higher. They've got more energy as they go round. So what else have we got? If we increase the voltage, I've just said that, you increase the current. You push harder, they've got more energy, they go round more quickly. So we increase the flow. If you actually put more of them through something, then that something is going to get more energy. So for example, a bulb will get brighter. Brilliant. Now, let's just try a quick poll to see who is listening. So I've got another question for you now. Let's see if you can remember which one was the flow of negative charge. Okay, so I just told you about some different measurements we use. Which one is the flow of negative charge? Very different this time. People not too sure, I think. About half of the people have voted. I might go back over that, I think. I'm going to give you another, we're nearly up to 100 people, so I like it. When we get to 100, then we've got at least 80% of people have voted. So I'm going to wait till I get there before I do anything else. So 99, brilliant, 100 people, 80% of people have voted. Right, the right answer was actually current. Current is the flow of negative charge. So I might just quickly nip back here, okay, and have a look at these. So the current is the flow of charge, the flow of negative particles or negative charge. The potential difference is the amount of energy that they've got. So potential difference, energy measured in volts, current, flow measured in amps. Okay, so when you come to read through these slides before you do your work, make sure that you have a really good look at this one with the definition on, because that's really important. And it looks like a few people didn't quite remember that. Okay, so circuit diagrams. One of the things that you're going to get set to do is at the end of this, for your week's work, is to draw some circuit diagrams. Now, you can draw them in Google Slides or another application like that, but it's actually probably better that you draw them on paper, even if that means that you can't hand them in, although you could take a picture using a camera on your computer or your phone and then add them to your slides so your teacher can see what you drew, because it's really good practice to get very good at drawing circuit diagrams in a very precise way. Now, the people that I teach that are here know that my drawings are rubbish. I am not an artist. I am very bad at drawing things. In fact, I should imagine there's a few people from ALTO laughing right now because they've seen my drawings. But one thing that I do is when I'm drawing a circuit diagram is I do always use a pencil and a ruler, because the lines must be straight. And this is the important bit, they must all join. If you don't join the lines, the wires aren't joined, so you haven't drawn a circuit. It's broken. It's really important. So don't rush them. No sketches, ruler, pencil, neat straight lines that join. Very important. You might have to draw a circuit diagram in your actual GCSEs, and it's a really good thing to know how to do. So how would we represent it? So here's our cell, and we represent that using this symbol. I'm going to give you a list of the symbols in a minute, so you don't have to try and memorize them. Don't worry. Wires we draw as straight lines, and we always give them a sort of rectangular shape because it makes it easy to lay everything out. And a lamp, that's the symbol for a lamp there. And you notice none of these lines overlap, but they all touch and they're all straight. And it's really important that you draw it like that, or it could in fact be wrong. And in your exam, it would get marked wrong, okay? It's really important that we draw them like that, because anyone who has got an electrician in the family or intends to become an electrician or an electrical engineer We draw really big, complicated circuit diagrams, and they are always drawn with straight lines that meet exactly. And that way, electrical engineers and electricians can actually follow the diagram and build the circuit for the house, the ship, whatever it is that they're building a circuit in, a car that they're building the circuit in. And it's really important habit. So it's not just for your exam. If you're ever intending to use this later on in life, you're thinking about being an engineer, an electrician, an electrical engineer, then you're going to, software engineer possibly even, you're going to need to be able to do that. So here are all of the symbols. Now, this is a task for you to do, and I'm not going to ask you to do it now. So what you're going to have to do, if you don't know them, you're going to have to look them up on Google and find out which symbol is which. And then you're going to have a list of all of the circuit symbols there. So, and you're going to need these because you're going to have to draw some circuits later on. So here are the two types of circuits that I said I'd teach you about today. Series circuits are number one. Series circuits are what some people sometimes call ordinary circuits. They are circuits that look like this one. It starts in one place. So here's the cell, and our electrons are off, and they go around, they go through that wire, through the bulb, up and round again. And there is just one single loop that goes all the way round. That's it, just one single loop. So we come back over here. It's one program after another. A series circuit is similar. If you follow it, you start in one place and you might go through lots of things, but you just go through one after another all the way round to the beginning. It's a little bit, if we imagine school, a series circuit is like going from the entrance to the canteen and walking all the way along the science corridor and then walking through maths, along the top corridor, past the staff room, to the stairs, back down into music and up to the entrance to the canteen again. One great big loop through each corridor in series. Science, maths, top corridor, music, round like that in series, one after another. Okay. Now, we could have multiple things in our series circuit. You could have one bulb, you could have two, you could have 3, 4, 50. As long as they come one after the other, and the electrons, the electricity, the current has to go all the way round through each thing, one after another in series. See where we're going there? All the way round, then it's a series circuit. And we draw them like this. So current in a series circuit. There's kind of a rule about current in a series circuit. The current in a series circuit is always the same everywhere. So how many electrons are flowing past will be the same anywhere that you look all the way round. So if this ammeter here reads half an amp, 0.5 A, that's the current there, then that means you've got 0.5 there, you've got 0.5 here, you've got 0.5 here, you've got 0.5 here. It is the same the whole way round, always. And the reason for that is the electrons have to go that way. There's nowhere else to go. They have to go through there, then that one, then that one. So the same amount are going to go through at each point all the way around. There is nowhere else for them to go. Potential difference is a little bit different because the amount of energy that they've got is going to change depending on how hard each thing is to get through. So it actually splits up as you go around. But I'm going to explain that a little bit more later. We're going to talk about potential difference going around circuits a little bit later. So thing to remember, potential in series circuits, the current is the same the whole way around. Right, here are some questions. Now, if, for example, you're in my class, you've probably done these questions already because we've done this far already. If you haven't, start with these questions. Do these questions first. So how do you do these questions? Remember, these slides are going to be shared in your classroom later on today, and you've got a whole week to do this work before the next webinar. So things I think we've talked about. We've talked about what a circuit is, that it's complete, it goes all the way around. We've talked about what current is, that it's a flow of negative charge or a flow of electrons. We've talked about what potential difference is. It's the amount of energy those electrons have got. We've talked a little bit about what happens. If they have more energy, they are able to make things for example, brighter, so they're able to do more work. We've also said that in a series circuit, current is the same the whole way round, and that a series circuit is one with one loop where each thing is one after another. So I think we've got there, and that's about halfway through this webinar. So that's mostly a recap for a lot of people of things that we've done before. So now I'm going to move on to something that's new. So let's just, these are questions for you to do later. So we're going to get rid of that, and we're going to talk about parallel circuits. Parallel circuits are brilliant. Parallel circuits are really, really important. They're also a bit more complicated than series circuits. So back in December, I put my Christmas tree up, and I put it up just there. You can't see where I am. I'm in my living room right now. Just over there, I put my Christmas tree, and I plugged it in. And what was fantastic is all of the lights lit up apart from one. One light didn't work. And I remembered being 10 years old, and my dad put a Christmas tree up, and he plugged in the lights and nothing happened. And he went, oh. He did that every single year, because every year we got them out and one of the bulbs had gone, and my dad had to get the spare bulb, take out the first one, put it in, turn them on. No, not that one. Take out the spare bulb, take out the second bulb, put it in, turn it on. Not that one. And he had to go through each bulb until he found the one that was blown and that had broke the series circuit, because remember, if a circuit isn't complete, nothing happens. And he had to find the bulb that had gone so that the lights came on. His lights were in series. Mine, where one bulb can go out and the rest stay on, parallel. And that's why we use parallel circuits. So let's have a look at what they look like. So here is a parallel circuit. So this is actually a set of instructions for setting it up as a practical. But what's important is the diagram. So I left the diagram on it. So here we see we've got our cell. There's our cell at the top. And we've got a wire loop that goes round to this bulb over here and back to the cell. And we've got another wire loop that goes from here round through this bulb. So now the electrons can, if they want, they can go, I've just moved the slide, they can go along here and they could go through that bulb and then go back up there and back. Or they could go down here and through this one. Now, obviously, if I took this top bulb and I broke it, this bottom bulb would still stay lit, because these wires touch there at that bit of metal. So the electrons can go around there and they can go down here, and that one would stay lit. If that one broke, that one would stay lit, providing it wasn't already broke. So the electrons can go either way. The current can choose to go down there or there. Okay. Now, that means the current can't be the same the whole way around, because half of it has to go this way and half of it has to go this way. So in a parallel circuit, the current splits up between the branches. Now, if both of these bulbs are identical, and I had 4 amps of current up here at the top, that means 2 amps would go that way and 2 amps would go that way. So it would split up. And when it comes back out the other side, I've got 2 coming up here, 2 coming up here, and it would join back together to be 4 amps again. So I've got 4 splits in half each way. Now, but there's a difference about the potential difference. If the electrons coming along here have all got 4 volts of energy, it doesn't matter if half of them go that way and half of them go that way. They all still have 4 volts of energy, okay, because that's how much they've got. So you still, the voltage, the potential difference, or the voltage across the bulbs, the potential difference is the same in every branch. A little bit confusing. Current splits up. It's the same in parallel. It's same in series, splits in parallel. Potential difference does it the other way around. It splits up in series, but it's the same in parallel. So we've only got 2 things to remember there. You might need to play this little bit of the video back again. In series, current is the same. In parallel, current splits up. In series, potential difference splits up. In parallel, it's the same. You might want to write that down. Those 4 things are very, very important. Okay, they are very, very important. So let's move along. So here comes the current. Let's look at it again. Here comes the current going down that way. So half of it will go down this one. And then the other half of it will go down here. It's a little bit like if we talk about the science corridor again. If you imagine all of the pupils walking along the science corridor towards maths, but half of them go straight along the top through maths on the top corridor, and the other half go down the bottom and walk along the languages corridor. And they go all the way past reception, past Mr. Deegan's office to the end. The other lot go all the way along the top, and they both get to those sets of stairs and come up together and walk back to the canteen. That's how that works in a parallel circuit. Half of the pupils went one way, half went the other way. The same number came back together. Okay, so that's how that current splits up going through there. Now, the voltage, or the potential difference, which is better, okay, the potential difference measured in volts is always the same anywhere that you measure it in a parallel circuit. Always, always, always the same. So let's just have a look to see who's been paying attention, and let's try another one of my polls. Let's have a look. Let's just talk about potential difference first. There you go, quick poll. Let's see.
Hello, sir.
Hello.
While they're doing the poll, I've had 2 questions. One I thought was quite interesting, and the other one I thought was good to clear up.
Okay.
In series circuits, is current the same, or is it parallel? Which one was it?
Right.
So a bit of confusion about that. And the other was, how many bulbs can you actually put on a circuit? I like
Good.
that one.
That's a very good question. Right, the first one, I hope I covered a little bit with what I said at the end of the last slide. Current series the same. Current in series is the same the whole way round. Current in series is the same. Current in parallel splits up. So that's what we do for current. There's 2 things you have to remember. Current in series the same. Current in parallel splits. That's your current. Potential difference in series splits. Potential difference in parallel, the same. So you've got to remember current, same splits. Potential difference, splits, same. So those are your 2 things. How many bulbs can you put in a circuit? I don't know that there's actually a limit to how many you can get in. What depends on is the resistance of those bulbs, the type of bulbs that they are, how much potential difference you've got, and your current. If you look at things like the Blackpool Christmas illuminations that have thousands upon thousands of bulbs all in them at once in parallel circuits, I should imagine that those are some of the biggest circuits that there are. So maybe that's something you could Google, the most number of bulbs in a circuit, but I should imagine it's well into the thousands. I'm going to end this now because it's been going for 2 minutes and nearly everyone voted. And the majority of people were correct that it was volts. Volts was the right answer for 3. So let's try another quick poll, another quick set of questions. I think we're ready for the next one. So that was really handy that question came in just now, Miss, because my next question, so I've just gone through series and parallel and what the current does. Let's see if you can remember it. Oh, we are doing well. You can remember it. This is fantastic. About 90% of people getting it right so far, and nearly everyone voted. Very, very good. Excellent. Good. Well remembered. The key to this is if you remember one thing, actually you can remember the rest because they're opposites. And so if you just remember one thing and remember that everything else is opposite, in series and parallel, they're opposites, it makes it really easy. So almost everyone's voted. So I'm going to close it now. And it stays the same the whole way around, which 84% of you got right. So most people got that right. So the easiest thing to remember is current, series, the same. And if you remember that sentence, actually, you can remember all of the other things because parallel is opposite. So current in series is the same. Well, that means the potential difference in series has to split up because they're opposites. And if current in series is the same, that means current in parallel splits. And so potential difference in parallel must be the same because we've got opposite, opposite. So I don't know if that will help you. It helps me remember it. I just remember current in series is the same, and then I can write out all of the others because I remember that we've got opposites in there as well, and that really helps me. So perhaps if I move that on, so these are some questions that I've got for you to do, but before we move on to that, let's just have another quick poll question to see how you're doing on this one. So you might need to read this carefully. When I put it up, PD stands for potential difference. PD stands for potential difference, voltage measured in volts. Okay, so let's have a look if you can remember them now, because remember I said series, current, the same, and then we've got opposites. See if that helps you. There's no race to fill this one in. I'm going to leave it up for a long time so that you can have a really good think about it. Current in series is the same. And then remember, we've always got opposites. So whatever current in series is, parallel is opposite. Whatever current is in series, potential difference in series is opposite. Got opposites each way. Right, I'm going to go over this one again, I think. This is interesting. Right. Quite interesting that quite a few people have chosen this isn't the answer. No, really it isn't. Don't click it. It really isn't the answer. 12 of you have chosen that one out of 138. It's quite interesting. We've got 79% of people have voted. So people are unsure and unhappy about this one. And it's about half between getting it right and not being sure. So I'm going to stop it. The answer was it splits up. It splits up. And what I'm going to do is I'm going to add another slide to this before I put it in with all of these in. So I'm going to put them all in another one, but there we go. So potential difference, the potential difference is the same across each. Oh no, did I just tell you the wrong answer? Miss, did I just tell everyone the wrong answer there? Poll 1, poll 5. Sorry, it's the same in each branch, not in splits up, it's the same in each branch. Okay.
Sorry, I was answering questions and all over.
No, I did. I said it splits up, and it's not true. It's the same in each branch. So potential difference is the same in each branch. So potential difference, same in parallel, splits in series. It might be worth writing. I wonder how many people know what a Battenberg cake is, Miss. I wonder how many of these students have ever eaten a Battenberg.
I had Battenbergs yesterday, the mini ones.
So a Battenberg cake, my granny always used to make me eat a piece of Battenberg cake every time I went round. And it's that cake that is, I'm just going to draw. Now, I've told you already that I'm rubbish at drawing, okay? But a Battenberg cake is a cake that when you slice through it, you've got a yellow piece and a pink piece in squares like this. Okay, so that's a Battenberg cake. Now, the Battenberg cake helps me remember my series and parallel, potential difference and current. And I'm going to show you how right now. And I'm just going to draw this. So I've made a little square there, and I've written series and para because I'm lazy and didn't write parallel. And I've written current and potential difference there. So series, parallel, current, potential difference. And I've got a Battenberg cake. Now I said you only have to remember one, because if you remember one, you have to then make it look like a Battenberg cake. So you do opposites. So I'm going to show you what I mean. So
some of them don't know what one is, and I went and got the box.
Oh, fantastic, Mix. Yes.
Yeah.
Yeah. Open your video. Fantastic. There we go, Battenberg cake. And you can see down in the bottom corner of Mrs. Thing, you've got a pink square and a pink square and a yellow square and a yellow square, like mini chessboard, all the way through the cake. Okay? So that's what my drawing was meant to be. And then because I've written series, parallel, current, potential difference, and I've written same in that box, all I have to remember is series, same, current, and then I can fill in everything else because I just do opposites. So that means that underneath I have to have a different color. So that has to be splits. And then over there, I have to have same, and I have to have splits because I've got to make my Battenberg cake. So I have to have same color, and splits and splits. So now I've got series, parallel, current, potential difference, same, splits, splits, same. And that's how I always write it out to help me remember it. Now, you might be neater than me, and I just scribbled that really quickly just now, but that might help you remember it. And you might want to play that bit of the video back, stop it, make your own flashcard neater and prettier than mine, maybe with a bit of Battenberg cake. Right, we've gone slightly over the time that I intended to take for this now, so I'm just going to explain. These are the questions. So I said you were going to get some things to draw. Okay, draw a series circuit with a cell and 2 lamps. Draw a parallel circuit with 2 cells and 2 lamps. Draw them neatly. You can do it on a Google document, on Google Slides, but if you are able, draw it on paper, take a photo and insert it onto the slide, because the better habit to be in is to hand draw it. Then you've got to check. Sorry, miss.
No, so I was just going to tell you I've got 2 questions.
Yep.
One is, what was it? What is a parallel circuit? So I think they were talking about the lines and the tracks.
Yep.
And then, are there any factors that limit the voltage across a lamp?
Yes, right. Let me go back to the parallel circuit. So a parallel circuit is a circuit, that's actually a good question, where there is more than one loop for the electrons to go through. So remember, in series, they had to go through the one loop all the way around. But this parallel one has got a second loop. It is able to go through that way. And I could add a third and a fourth and a fifth loop. So I would just draw another box underneath and another box underneath. So a parallel circuit is one where there is more than one path for the electricity to go. So here we've got 2 paths, but we could draw another line across there with another lamp in the middle across there, and then we'd have 3 paths. We could put another one here and we'd have 4 paths, and we could keep going. Okay, so a parallel circuit has got more than one path. It can choose which path it is going down, if you like. Okay, so that's a parallel circuit. And is there a limit to the voltage across the bulb? Yes, because the voltage, remember, is the amount of energy that those negative charges are carrying. And they make the bulb glow because they push their way through it, and the bulb, the filament in these type of bulbs we use in school, starts to glow because it's getting hot, because the energy is being transferred to the filament. And if we give it too much energy, we will melt the filament and the bulb will do what we call blow. In our energy saving bulbs, it works a little bit differently, but the same principle would happen. If we put too much energy transfer through it, we would break it. So there is a limit, and bulbs normally have a rating on them. So these ones that we use at school say on the side of them 12 volts. If you put much more than 12 volts through them, they break. The ones in your house are 240 volts. If you put much more than that through them, they would break. And so there is a limit for each bulb. So here are your questions. The drawing, I've suggested you do it on paper if you're able. If you can't, that doesn't matter. There are some things for you to look up and some questions for you to answer there about the things that I've just talked about that will let your teachers know whether you've understood it. The next bit, now this is challenge, although I think year 8, you are a particularly good year. You talk to any of the science teachers and we always go, oh, year 8, okay, because your year group are particularly good at science. So I think quite a lot of you could probably do this. And it's to make a slide. Now you can either make a Google slide or you could draw something on paper if you prefer flashcards or you prefer doing that kind of thing, and perhaps take a photo of it and upload it instead. But let's get some real technical descriptions going on here. Let's include a definition of what current and potential difference are, and then say what happens to each one of those as they go around a series and a parallel circuit. And it says you must include a diagram, which means you have to draw a circuit diagram of a series circuit and a parallel circuit to be able to explain it properly. Okay, so things I think we've covered: what a circuit is, what current is, what potential difference is, the difference between series and parallel, and what happens to current in series, and what happens to current in parallel, and what happens to potential difference in series, and what happens to potential difference in parallel. And there are a series of questions at the end to help you show that you understand that. If you don't completely understand it, I suggest you watch the video back. Also have a read of the slides and see if that helps you. I'm going to stay here for a moment, see if there are any more questions that I need to answer. And then I'm going to end this. So I'm just going to stop recording it for a moment because we don't need to answer any of those. So